Okay. The idea of this little tutorial is to explain maybe a little bit more detail what happens when you want to extract acidic compounds. And in fairness, it's exactly the same for alkaline or basic compounds, but we'll review them very shortly and more concisely in the end. So what happens when you have to extract acidic compounds? Well, acidic compounds dissociate, so they have a dissociation constant, Ka, which is the ratio of their conjugated base concentration times proton, H+. That could be H+ or H3O+, doesn't make any difference, over the concentration of the acid, AH. That is just the equilibration the equilibrium constant Ka of this equilibrium here. So it's product divided by reagents. And we also have a distribution or a partition coefficient Kd between Ha in the organic phase here in phase 2 over AH in phase 1, which would be water. So Kd is equal at concentration of the acid AH in phase 2 over that in phase 1. But those two equations and those two equilibria are intrinsically linked. So if, for example, we push AH away from its equilibrium towards the more dissociated A- compound, we're going to pull the equilibrium here to the right, and by reducing the amount of AH or the concentration of AH in phase 1, we're going to pull the concentration, this equilibrium here, downwards. So we're going to pull the concentration of AH from phase 2. So by changing the pH here, we can see that we can pull the equation towards the formation of more conjugated base and reduce the concentration of AH in phase 1, which will pull the concentration of AH from phase 2. So those two equilibria are intrinsically linked. The problem that we have so far is that we don't really know how they are linked and what to do with those two kind of complicated equations. And also in real life, Kd is unknown. What we know is an apparent distribution coefficient or distribution ratio D, which would be the concentration of AH in phase 2 over the concentration of AH in phase 1 plus the concentration of A- in phase 1. In fairness, if we could also have concentration of A- in phase 2, but we know that by definition an acid cannot dissociate in an organic solvent, so there's no dissociation in organic solvent. So A-2 is equal at 0. That we can calculate, that we can measure. D is measurable. And also Ka is well measurable. There are tables. You can actually look for most organic acid, you will have the dissociation constant tabulated. So how do we link D to Ka, and how can we influence the apparent distribution or partition coefficient and how can we modify it with pH? So it is a function of pH. And how is it a function of pH? Well, the first thing that was asked of you is to rewrite this equation of D as a function of H+. So let's rewrite that. So if I go back and rewrite, what do we start with? We have Kd, which is equal at AH2 over AH1. We have Ka, which is equal at M minus times H plus over AH, and that is always in phase 1. And we have D is equal at AH 2 over the sum of all the forms of A in phase 1, so it's AH1 plus the concentration of A minus in phase 1. Well, concentration of A minus in phase 1 is equal at Ka AH phase 1 divided by H plus, so that the sum here, the AH phase 1 plus concentration of A minus in phase 1, can be simplified by AH phase 1 plus Ka AH over H plus. So that's AH in phase 1, and I can put all that together as 1 plus Ka over H plus. So I can re-inject that here in D, and D is equal at AH2 over that sum here, and that sum now is equal at AH1, so AH1 times 1 plus Ka over H plus. Now I can note that this ratio here, AH2 over AH1, is equal at Kd. So we have D is equal at Kd over 1 plus Ka divided by H plus. I can maybe not simplify, but at least clean that up a little bit by multiplying top and bottom by H plus. So it's Kd H plus, and then if I multiply the bottom also by H plus, it's H plus here plus Ka. So you have what you are given in your notes, so that D is equal at Kd H plus over H plus plus Ka. All right. Now you're asked what happens when pH is equal at pKa plus 2. Well, we don't have pH or pKa in those, but we know that H plus is equal at 10 to the power minus pH, and we also know that Ka is equal at 10 to the power minus pKa by definition. So we know that 10 to the power minus pH is equal at 10 to the minus pKa minus 2, and that is equal at 10 to the power minus pKa times 10 to the power minus 2. And then 10 to the power minus pKa, we know it's Ka, and 10 to the minus 2, well, it's 1 divided by 100, so it's 0.01. So writing pH is equal at pKa plus 2 means that H plus is equal at 1/100th of Ka. So if I look at that original here, D, Ka plus H plus, well, H plus is very small, and so D is equal at KdH plus divided by Ka. And that is basically about 0.01 Kd, so it's close to 0. So for pH is equal at pKa plus 2, which is at high pH conditions, the apparent distribution of an acid is equal at 0. We can do the opposite. We can look at low pH condition, where pH is equal at pKa minus 2. So it's low pH conditions. Well, we can redo exactly the same thing. 10 to the power, so H plus is equal at 10 to the power minus pH is equal at 10 to the power minus pH, pKa plus 2 is equal at 10 minus pKa times 10 to the power 2, so it's Ka times 100. This time, at low pH, the concentration of H plus is equal at Ka times 100. So we can rewrite or simplify D as saying that D is roughly equal to Kd H plus over H plus, so is equal at Kd. So at low pH conditions, D of an acid is equal at Kd. And last, you are asked to do what happens at pH is equal at pKa. Well, this time it doesn't take too long to say that 10 to the power minus pH is equal at 10 to the power minus pKa. So H plus is equal at Ka. D is equal at Kd divided by 2. And we can put that together as a graph, as it were, and we can try to see what D and how does it varies with pH for an acid. Well, we know that at very high pH, when pH is equal to pK plus 2, D is going to be roughly 0. So you're going to have something that's going to be quite low here, near 0. And at very low pH, pK minus 2, D is equal at K. Kd. And in the middle, at pH is equal at pKa, D is equal at Kd divided by 2. So we're going to have something a little bit like that, where K is going to go down, and it's going to be a bit of an inverse curve. It's not very nicely done here, but where D varies with pH, being maximum at low pH. So and D is minimum or equal at 0 at high pH. Sorry, at high pH. And in the middle, D is equal at Kd divided by 2. And this follows very much what we saw last year in second year, but it's also, I mean, the classic thing about acid-base dissociation or competing equilibria is that if we think about it in terms of dissociated and undissociated forms of the analyte, we know that depending on pH, we have at low pH all the acid is in the acid form and becomes more and more ionized as the pH is raised to become its conjugated form or conjugated base form. I'm not going to put concentrations here. But the predominant species at high pH is the conjugated base, which is negatively charged. It has deprotonated, and at these high pH conditions, this form cannot partition with an organic phase because it's dissociated. It's very hydrophilic. At low pH, the protonated form of the acid, AH, is neutral and can dissociate. This one can dissociate, can partition with AH in the organic solvent. This one can't partition because there's no A- in organic solvent. That doesn't exist. So the only way for an acid to partition is for it to be in in the neutral form, protonated form, so that is at low pH. Conversely, on the opposite, if we think about what happens when we have a base, well, a base with pH is the opposite as the acid, in the sense that we have still a protonated form of the base at low pH and a deprotonated base B at high pH. That is the base, that is the conjugate. BH plus is the conjugated acid. This time the conjugated acid cannot partition with the organic solvent because the protonated form is not soluble in organic solvent, but the neutral form of the base B can dissociate, and that equilibrium, so at high pH, the base will partition. I'm going to write that down. Bases partition to organic solvent because they are in neutral forms. All right, I hope that helped, and we'll see more of that over the course of the semester. I'll see you then. Goodbye.